Assalamualaikum and good evening to fellow viewers. We are from Group 1 and today we'll be presenting about experiment 8, which is heat transfer coefficient in dropwise and film condensation. So for the introduction of this experiment, we can see that dropwise condensation and film condensation are the two types of condensation. Filmwise condensation forms a continuous liquid film on the surface, but dropwise condensation forms small droplets. In general, the condensation forms dropwise or filmwise on the surface are determined by the surface wettability. So dropwise condensation is a discrete phase transition which process in which droplets grows in random sites on the surface and then coalesce and depart. Firm condensation occurs when the temperature of a vertical, impermeable, and wettable wall next to a porous medium saturated with vapor falls below saturation temperature. Okay, so the objective of this experiment is to define the condensation process. Number two is to determine the heat transfer coefficient for the dropwise and film condensation using the condensation process demonstration unit. And the number third is compare the condensation process between the two different materials. For the scope, we have to manipulate the flow rate using naked eye to observe. And then we evaluate the heat transfer coefficient in dropwise and film condensation with different volumetric flow rate. Okay, so for the theory, firmware condensation is a prime example of copper, and when the liquid wets the surface, spreads out and forms a film, this process is known as firmware condensation. And for the dropwise condensation, which prime examples of gold, if the surface is not wetted by the liquid, then droplets form and run down the surface, and this process is also known as dropwise condensation. And for generally, when vapor comes in contact with surface, having temperature lower than saturation temperature, the condensation will occur. Carry on with the theory for the formula. So the formula related to heat transfer coefficient alpha is alpha in bracket of for the unit is W over m to the power of squared theta c and is equal to Q over A Ts minus Tw, where Q for the unit is J over S is equal to transferred thermal power. And then we can see the specific heat capacity, which is Q for the unit is J over kg degree Celsius is equal to mass flow rate times C times P and in bracket of T out minus T in. So that is the specific heat capacity of water. And then we have the A in bracket of m to the power of 2 is equal to condenser of surface area. And then Ts minus Tw for the unit is degree Celsius, and that is equal to temperature difference between the saturated vapor and the wall of condenser.
This is the experimental setup. There are many main components: B1 tank, B2 condenser separator, P water jet pump, W1 condenser for film condensation, W2 condenser for dropwise condensation, W3 cooler, W4 electric heater, V1 cooling water valve for film condensation, V2 cooling water valve for dropwise condensation, V3 pump valve, V4 filling and drain valve, V5 condensate valve, V6 ventilation valve, V7 safety valve, V8 ventilation valve. F1 flow meter for film condensation, F2 flow meter for dropwise condensation, P1 tank pressure, T1 film condensation inlet temperature, T2 film condensation outlet temperature, T3 film condensation surface temperature, T4 dropwise condensation inlet temperature, T5 dropwise condensation outlet temperature, T6 dropwise condensation surface temperature, and the last one, T7 tank temperature. Methodology. The first one, we will switch on the main power source and then open the pipe water. Then switch on the heater water 6. After, repeat the steps 6 and 7 with the flow rate 6, 9, 12, and 15 liter per hour. Observe the water droplets from copper and gold. Safety procedures. Make sure the main switch is turned off when switched on the main power. Reason: to avoid short circuit. Solution: double check whether the main switch is switched off before switch on the main power. The next one is avoid touching the tank when it is heated. Reason is it will cause injury because the temperature is too high. Solution: wear gloves when the experiment is conducted. Adjust the cooling water valve V1 and V2 slowly to control the flow rate. Reason: to get a precise value. Solution: turn the cooling valve while observing the flow rate that we want, slowly until the flow of water is not too big and too small.
Next, we move on into the result and calculation part. For the first part, we have table 1, film-wise condensation. This is the table of the film-wise condensation. This table we label it as a table 1. In this table 1 contains the volumetric flow rate that we set at plus minus 3 liters per hour, the data that we collected from T1, T2, T3, T7, and the data that we calculated. It is a mass flow rate, transfer thermal power, and heat transfer coefficient. For the next part, we have table 2, Dropwise condensation. This is the table for the Dropwise condensation. We label it as a table 2. So, the table 2 contains the volumetric flow rate that we set at plus minus 3 liters per hour, the data that we calculate, that we collect from T4, T5, T6, T7, and the data that we calculated also it is a mass flow rate, transfer thermal power, and heat transfer coefficient. For the next part is a calculation part. So first, we have the calculation of the film-wise condensation. We have 3 formula that we use in this experiment. First, we have the mass flow rate, and second, we have transferred thermal power, and third, we have heat transfer coefficient. So, this is all the formula that we use to calculate the mass flow rate, transfer thermal power, and heat transfer coefficient for the film-wise condensation part. Next, we have the calculation for the Dropwise condensation part. Also same, we have mass flow rate, transfer thermal power, and heat transfer coefficient. So, for this part is the calculation to calculate mass flow rate, transfer thermal power, and heat transfer coefficient for the Dropwise condensation. For the next part, we have graph. So, this is the graph 1, film-wise condensation. We can see that graph 1 shows that the increasing of heat transfer coefficient along with the increasing of volumetric flow rate that we have set at plus minus 3 liters per hour. This graph is a volumetric flow rate against heat transfer coefficient for film-wise condensation. For the next graph, we have graph 2, Dropwise condensation. For the graph of Dropwise condensation, we use the volumetric flow rate against heat transfer coefficient for Dropwise condensation. From the graph 2, we can see that graph 2 show that the increasing of heat transfer coefficient along with the increasing of volumetric flow rate that we have set at plus minus 3 liters per hour. Compared to the first graph, is graph 1, we can conclude that graph 2 have the high heat transfer coefficient than the graph 1.
This is the observation from the experiment and from the graph. As we can see from the observation, it shows that copper has a very visible water droplets. However, gold doesn't have that kind of very visible water droplet. This is because there's a film coating the layer of copper that allows water droplet to stick on it first before it fell down. Next, if we were to compare graph 1 and graph 2, it shows that dropwise condensation has a higher heat transfer coefficient. Gold here represents the dropwise condensation, while copper here represents the film-wise condensation, as we can see from the droplets stick on the copper rod and the gold rod. The water droplet can stick on the copper rod because the film around the copper rod causing heat resistance more than gold, which will be resulting in the difference of heat transfer coefficient, which also means that less heat will be on the copper rod, which allows the water droplet to stick for a while on the copper rod rather than the gold. As a conclusion, we can conclude that condensation is a process where water vapor turns into liquid water. We can also see that dropwise condensation has higher heat transfer coefficient rather than film condensation. And lastly, gold has higher heat coefficient due to no film layer to resist the heat outside of the rod. From the calculation, we can also prove that the heat transfer coefficient for dropwise condensation is higher compared to film-wise condensation. These are the references used for our lab report. Thank you.